Hi everyone, I'm Connor,
And I'm Dan.
and today we're going to be talking to you about distributed climate control. Heating and cooling systems as a technology have existed since the beginning of the previous century. Over time, there have been improvements reducing the amount of power needed to use these systems in an effort to reduce the amount of energy, costs, and power needed to use these systems. However, even with these improvements, HVAC still takes up half of commercial and home energy costs in the United States. Why is that? We have found that the reason behind this is that HVAC in its current form is very room-oriented, meaning that the most specific thing that an HVAC system can target is a single room. According to ARPA-E research, 15% of energy from HVAC systems is wasted because of this. Whether a room has many or few people, there is a significant amount of heating and cooling applied to the same room. Our solution to this is DCC, where we aim to determine where and how many people are in a room using a system, and using that information, we provide HVAC only where needed. Additionally, we can control temperature automatically by continuously scanning a room to find how many people are in there. We can save money and energy in the long run using this solution. Now, I'll let Dan get into how the system actually works and what it is.
Thanks, Connor. Here's what the system looks like now. We've got a fluoropton thermal camera connected to a Raspberry Pi. The Raspberry Pi acts as a server to send thermal images to our Windows machine. We're using a Connect V2 sensor, which gives us color images and can also function as a depth sensor, which we're hoping to incorporate in the future. Lastly, there's an Arduino which drives servo motors to pan and tilt the entire system. This allows us to take multiple images and stitch them together to get a full view of the room to make up for the limited field of view of the thermal camera and Connect. Here's a demo of its current functionality. As you can see, the motors are driving the machine head to take multiple images. Our command line tells us our server is working properly, and at the end the images are stitched together and we run our detection on it. Here we can see Conor is detected on the 4th floor of the GWSCH. Here's a closer look at what the images look like once they're finally stitched together. Let's hear from Conor about how this actually works.
Thanks, Dan. So the first step in the main processing section of DCC is panorama stitching of our color images. We do this for a few reasons. One is that the color camera that we use does not have a wide enough field of view to capture the full scene of that we want to capture. Additionally, it is much more difficult to capture a person tracking through multiple images and figure out where in the room that is, than to stitch it all together and just determine based off of that one image where it is. For example, looking at these two images on the screen, we have two shots of the same lab taken at slightly different angles. We have one subject that is present in both frames. If we try to apply person detection to each of these images individually, it would be hard to determine whether this was one subject or two based off of that. However, as we'll show you, through panorama stitching, we can determine this is in fact just one person. The first step in our panorama stitching algorithm is to extract and match scale invariant descriptors. We do this using a SIFT algorithm, which stands for Scale Invariant Feature Transform. Once we extract these descriptors, we match them up, and using a ransack algorithm, we place them in a homography matrix. Using a homography matrix allows us to track objects, whether they have been rotated or otherwise transformed. Once we have this homography matrix, the last step is to apply a warping transformation to one of the images. We treat one image completely statically and leave it as a baseline for the rest of the panorama. The other image is applied a warping transformation according to the homography that we just created and placed next to it such that it lines up. So as you can see here, the left image is the baseline, is not changed, and the image on the right is warped so that it matches it perfectly. The next step is to apply stitch together our thermal frames. We need to use our thermal information as a cross-reference, basically, for our color images. If we find a person in our color images, we want to say, hey, there is also a person in the color, so it is in the thermal, so it is definitely a person. There are some issues associated with this. One is that the thermal camera does not have as much information to extract as color camera. This is because the thermal camera only tracks hot and cold, and in a room there's typically a lot more cold than there is hot, so it can just generally blend together. Our solution to this is to apply the same color transformations that we found using the homography to our thermal data.
However, there's one problem that arises here. The thermal field of view and resolution is less than that of the Kinect. To make up for this problem, we're actually cutting pixels off the sides and top of the Kinect frame to match the field of view of the thermal Lepton camera. Then we're upscaling the resolution of the thermal frame using pixel sampling so that it matches the Kinect field of view and resolution.
As you can see, once we apply the same homography from our color images to thermal, we get an almost identical panorama stitch of our room. The only differences are related to the slight different positions in each of our cameras. Regardless, we can get consistently matching panorama stitches that are ready for accurate person detection, which Dan will get into now.
Thanks, Connor. So when it comes to detecting people in images, there's two main things to consider. The first is a feature descriptor, and the second is a classification model. For our feature descriptor, we're using histogram of oriented gradients, or HOG. The way HOG works is by cutting up images into small subsections. Each of those subsections is summarized by the overall gradient of the pixels in that subsection. The subsections together tell us what the shape of an object in an image looks like. This is very effective for object detection and is actually used in the SIFT algorithm that we mentioned earlier for our panorama stitching. Now that we have a way to describe how people look like mathematically in an image, we need to determine whether or not the mathematical construct that we're looking at is a human or not. We're doing this with a support vector machine, and specifically a linear support vector machine. That means that there's a linear margin determining whether or not our prediction is going to be positive or negative, or in this case, a human or non-human. To do this, we've trained on positive and negative training sets, which contain images of people's heads, shoulders, or full bodies, depending on what type of model is being trained. This is effective, and the training is done prior to real-time running so that the predictions can be made fast and accurately. When it comes to our project's future, there's several things to consider. The first is whether or not stitching in multiple cameras is viable in a real-time setting. Right now we're using image stitching, which means that we're taking multiple images and then putting them together and tracking on the same image, or detecting on the same image. In the future, we might try to use multiple cameras and synchronize them in order to make up for the problems that arise from using a single camera, which is a small field of view as well as limited perspective. Additionally, we have yet to use the Kinect depth sensor in order to situate where people actually are in a room. While it's not super long range, it could be effective for a small room, determining where people are, and then managing HVAC systems for microclimate zones. Lastly, having a head count makes our system very applicable to building automation. What this means is that knowing how many people are in a room at a time allows you to predict how many people will be in a room in the future. In other words, if you use a conference room at a certain time every time of week, or if people enter the cafeteria at every time of the week, you could pre-cool the room or preheat the room so that it's comfortable when people enter. Then when they leave, it will automatically turn off, so that energy is not only saved, but also the work environment is always comfortable for people in the room.
So, now that you've heard from Dan about some of the technical implications and questions with DCC, let me tell you about some of the commercial environmental impacts that we can provide. That 15% of energy that was wasted before can be drastically reduced using DCC-related technologies. Additionally, greenhouse gas emissions from HVAC contribute to 13% of it in the United States. Using technology such as ours, we can reduce that by 2% to just 11% of greenhouse gas emissions in the United States. So today we've hoped you've taken away some information on how DCC can help bring HVAC into the modern era.
I'm Dan.
I'm Connor.
And we are Distributed Climate Control. Thank you.